The largest volcanic eruption on Earth so far this year is one almost nobody is talking about, and that is because you cannot see it. It is underwater, remote, hidden beneath the Central Bismarck Sea near Papua New Guinea. But three completely separate instruments, earthquakes, sound, and satellites, are all telling the same story about Titan Ridge, and the story is escalation. It launched a steam column 9,000 feet into the sky while still submerged. It is getting more powerful by the day. In this video, we decode what the satellites are seeing, why the depth of this volcano is the biggest unanswered question, and how an eruption you cannot even see could still reach a distant shore. If a story like this one keeps you curious, subscribe to the Quiet Archivist, because this eruption is still unfolding, and we will be following every move it makes. Drop a comment telling me whether you think Titan Ridge ends as a new island or a disaster. Now, let us get into it. Somewhere in the open water north of Papua New Guinea, the ocean is doing something it has only let us watch a handful of times in all of recorded history. It is building land. Right now, beneath the surface of the Central Bismarck Sea, a volcano is erupting, and it has been erupting for more than 2 weeks without pause. It is not slowing down. It is not settling into a quiet rhythm the way most of these underwater eruptions eventually do. It is doing the opposite. Every measurement we have, every signal we can pull from that stretch of sea, is pointing in the same direction, and that direction is up. The eruption is getting stronger. The energy behind it is climbing. And if the pattern we are watching holds, we may be looking at the birth of a brand new island, forming in real time, on a planet where that almost never happens, where anyone can see it. This volcano is called Titan Ridge. That name comes from a local pronunciation, and it sits in the Central Bismarck Sea, not far from Papua New Guinea, in one of the most geologically restless corners of the entire planet. And here is the thing that should make you lean in. Watching an island being born is genuinely rare. In the entire satellite era, the era where we have eyes in orbit capable of photographing a patch of remote ocean day after day, we only have a small number of clear examples of this process unfolding from start to finish. Scientists around the world are paying close attention to Titan Ridge for exactly that reason. This is not a routine eruption. This is a chance to watch a piece of the Earth's crust assemble itself, and that opportunity does not come around often. But there is a second half to this story, and it is the half that turns wonder into something colder. The same eruption that might build new land is also accumulating an enormous amount of energy in a structure that is fundamentally unstable. As a submarine volcano grows, as it stacks rock and ash and lava upward from the seafloor, it builds a steep, loosely assembled cone. And steep, loosely assembled cones in the ocean have a tendency to fail. Part of the structure can break away and slide. When that happens underwater, it displaces a staggering volume of seawater all at once. And that displaced water has to go somewhere. It goes outward, as a wave. The Bismarck Sea has a long, documented history of exactly this kind of event. Landslides and collapses that have generated tsunamis. So the question hanging over Titan Ridge is not a small one. We may be watching the creation of an island, or we may be watching the slow loading of a geologic disaster. And the unsettling part is that those are not two separate possibilities. They are the same process, seen from two different angles. Let me take you back to the beginning, because the timeline tells you a lot. This eruption started up on or around the 8th of May in the year 2026, and it did not start quietly. In the days right before the eruption became visible, the seafloor in that area began to shake. There was an earthquake swarm, a tight cluster of quakes grouped close together in both time and location. If you pull up the earthquake mapping tools that the United States Geological Survey makes public, you can see the whole sequence laid out. The earliest significant events struck right around the 8th of May. There was a magnitude 4.6, then a 4.7, then another 4.6, and then a 5.6. 4 earthquakes clustered tightly, all in the same patch of sea. Now there was also a separate 5.7 that struck a little farther away, and the analysts looking at this consider that one unrelated to the swarm, so we set it aside. But that opening burst of activity, the 4.6, the 4.7, the 4.6, the 5.6, that was the ground announcing that something was on its way up. What does an earthquake swarm like that actually mean? It means magma is moving. When a body of molten rock pushes its way up through the crust, it does not glide smoothly. It cracks things. It forces the rock around it to fracture and shift, and each one of those fractures, each violent adjustment, registers as an earthquake. So a cluster of quakes that tight, in a spot with no recent history of that kind of shaking, is one of the clearest signals geologists have that magma is on the move, and an eruption may be imminent. And then, right on cue, the eruption began. The sea above Titan Ridge started to change. After that opening burst, the activity cooled off for a little while, but it did not stop. On the 15th of May, a magnitude 5.4 struck. On the 17th, a magnitude 5.1. The volcano was not done. And then came the 22nd of May, and the single most important data point we have so far. On that day, a magnitude 5.7 earthquake struck the swarm. That 5.7 is the strongest earthquake in the entire sequence to date. And as you are about to see, the fact that the biggest quake came late, well after the eruption was already underway, is not a detail you can wave off. It is the whole story. Because in the world of earthquakes, a number like 5.7, arriving when it did, is not just one more entry on a list. It is the ground telling us that whatever is happening down there is not winding down. It is winding up. And to understand just how much energy that single quake represents, we have to talk about how earthquakes are actually measured, because the scale hides something that most people get wrong. Here is something that almost nobody outside of seismology really internalizes, and once you understand it, the Titan Ridge story snaps into a much sharper and much more alarming focus. The scale we use to measure earthquakes is not a normal, evenly spaced scale. It is logarithmic. That word gets thrown around a lot, so let me make it concrete. When you move up the magnitude scale, you are not adding energy. You are multiplying it. Each whole step up the scale represents roughly 32 times more energy released. A magnitude 6 is not slightly stronger than a magnitude 5. It releases on the order of 32 times more energy. A magnitude 7 releases roughly 1,000 times more energy than a magnitude 5. The numbers look close together. The reality they describe is anything but. So let us apply that to the Titan Ridge swarm. We had that opening cluster around the 8th of May, the 4.6, the 4.7, the 4.6, the 5.6, then the 5.4 on the 15th, then the 5.1 on the 17th. If you take all of those earthquakes, every single one that preceded the 22nd of May, and you add up the total energy they released, you arrive at a certain figure. And here's the part that should stop you. The single magnitude, 5.7, that struck on the 22nd of May, released, all by itself, roughly the same amount of energy as that entire earlier sequence combined. One earthquake, one day. As much energy as everything that came before it, stacked together. Think about what that actually tells us. If this eruption were a normal one, the kind that flares up and then gradually fades, you would expect the earthquakes to follow that same arc. You would see them grow weaker over time as the system relaxed and the pressure bled off. That is the textbook pattern for an event that is calming down. Titan Ridge is doing the exact reverse. Its largest energy release came late. It came after 2 weeks of eruption. The system did not relax. It loaded. Whatever is feeding this volcano delivered a fresh, massive surge of energy on the 22nd of May, and it delivered it in a single, concentrated event. That is not the signature of an eruption that is running out of fuel. That is the signature of an eruption that just got a new tank of it. And the earthquakes are only one of the instruments telling us this. There is a second, completely independent line of evidence, and it comes from sound. The ocean is an extraordinary carrier of sound. Noise travels through seawater far better and far farther than it does through air, and that means an underwater eruption is, in a very real sense, audible. It generates what scientists call a hydroacoustic signal, sound waves rolling out through the water from the eruption site, and we listen for those signals. We have instruments that do nothing but listen to the deep ocean. The Mineral Resources Authority of Papua New Guinea, the agency responsible for monitoring exactly this kind of event in that region, reported something specific. At 3 in the afternoon on the 20th of May, there was an abrupt rise in the hydroacoustic signal coming from Titan Ridge. Not a gradual climb, an abrupt rise. The volcano, in effect, suddenly got louder. Now hold those two facts next to each other. On the 20th of May, the volcano abruptly got louder. 2 days later, on the 22nd, the strongest earthquake of the entire swarm struck. Those are two different measurement systems, sound and seismicity, operated and interpreted independently, and they are telling the same story with the same timing. The Mineral Resources Authority noted that the sudden jump in hydroacoustic signal could indicate an upsurge in the volcano's activity. The 5.7 earthquake that followed it reads like a confirmation written in a different language. When two unrelated instruments, measuring two completely different physical phenomena, both point at the same conclusion within the same 48-hour window, that conclusion stops being a guess. It becomes the most likely truth, and that truth is simple and stark. Titan Ridge is escalating. This is the moment to be honest about what makes this story so compelling and so genuinely uneasy at the same time. Most submarine eruptions are quiet stories. They flare, they fade, and the ocean closes back over them, and almost no one ever knows. This one is refusing to follow that script. It has the staying power of a long eruption and the rising intensity of a young one, both at once, and that combination is unusual. It is the reason scientists are watching, and it is the reason the word escalation keeps coming up. Because escalation in a volcano is a loaded word. It points two directions at the same time. It points toward a structure tall enough and persistent enough to break the surface of the sea and become permanent land. And it points toward a structure carrying so much energy, growing so fast that its own steep flanks become a danger. To see how both of those futures grow out of the same root, we need to go down beneath the seafloor into the plumbing that feeds a volcano like this. Because the engine driving Titan Ridge is more intricate and more revealing than the word magma chamber would ever suggest. When most of us picture what lies beneath a volcano, we imagine something simple. A giant cave filled with glowing liquid rock, sitting and waiting until the day it bursts. For a long time, that was roughly the scientific picture too. But the research on magma plumbing systems over the last couple of decades has taken that simple cartoon and replaced it with something far stranger, far more complex, and far more useful for understanding what Titan Ridge is doing right now. There is no single cave. There is a system, a layered, intricate architecture of rock and partial melt. And once you understand how it works, the earthquake swarm and the escalation stop being mysterious and start being readable. Let me walk you through it the way the current science describes it. Down beneath a volcano, the crust is not a uniform block, and it is not a uniform pool of liquid either. It is a patchwork of different states. In some places, you have what scientists call melt lenses. Picture a lens, the shape of one, a thin, concentrated pocket. A melt lens is a region where the rock is genuinely, highly molten, a pool of true liquid magma, very high in melt content. But those lenses are not the whole system. Surrounding them and threaded between them, you find something different. Crystallized mush zones. A mush zone is exactly what it sounds like. It is a slushy, partly solid, partly molten mixture. It is not pure liquid, and it is not solid rock. It is somewhere in between, full of crystal structures, minerals like plagioclase, that have already begun to grow and lock together, suspended in a smaller fraction of melt. And then, in still other places, you have rock that is essentially hard. Crust that holds very little magma at all, mostly solidified, structurally stiff. So the engine beneath Titan Ridge is this three-way patchwork. Pockets of true liquid, zones of crystal slush, and blocks of solid, stubborn rock. Now here is where it gets dynamic, and here is where the earthquakes come back into the picture. Imagine a fresh pulse of melt rising up from the mantle, from deep down in the earth, pushing its way into this system. That new, hot liquid arrival does something dramatic. When it reaches one of those crystallized mush zones, it can rapidly reactivate it. It heats the slush, adds fresh liquid to it, and remobilizes a region that was sitting there half frozen. And if those mush zones are already well filled, already primed, that fresh pulse can cause them to discharge, to let go. All of that remobilized material can move together at once, and that is the recipe for a large eruption. It is not a single cave emptying out. It is a network of slushy reservoirs getting kicked awake by a new arrival from below and surging upward in concert. That is almost certainly what we are watching at Titan Ridge. The earthquake swarm, that opening cluster around the 8th of May, was the signature of a substantial push of magma forcing its way up through the crust, cracking rock as it went. The magma moved, the crust fractured, the quakes registered, and the eruption that followed is that magma reaching the surface of the seafloor and expressing itself. But there is a subtler layer to this, and it is the layer that explains why the volcano is getting stronger instead of weaker, and it has to do with what the earthquakes themselves do to the system. We tend to think of earthquakes as symptoms, as the alarm bell that tells you magma is moving, and they are that. But they are also more than that. Earthquakes are active participants. When an earthquake ruptures the crust, it creates new fractures. It opens and extends cracks. It builds out fracture zones. And those fresh fractures become pathways. Magma flows into them and fills them. In one sense, that is a relief mechanism. The system has more room now, more space for the molten rock to occupy, and that can bleed off some pressure. But look at the other side of that coin. By filling those new fractures, the magma has just enlarged its own reservoir. The total connected volume of melt in the system is now bigger than it was before the earthquakes. And here is the trap. If another pulse of magma now arrives from depth, and remember, a pulse from depth is very likely what generated the earthquakes in the first place, that new pulse is no longer feeding the original, modest system. It is feeding an enlarged one, a bigger reservoir, freshly connected, freshly primed. And a bigger primed reservoir means the potential for a bigger eruption. Do you see the loop? Magma rises and triggers earthquakes. The earthquakes crack the crust and extend the plumbing. The extended plumbing fills with magma and grows the reservoir. And the grown reservoir, when the next pulse arrives, can produce something larger than what came before. This is not a system winding down. This is a system that, with every surge, builds the capacity for its next surge to be greater. It is worth slowing down on why this matters so much for Titan Ridge specifically. A great many submarine eruptions are essentially single events. A pocket of magma reaches the seafloor, empties itself out, and the eruption ends because the fuel ran out. That is the ordinary case, and it is why most underwater eruptions are short. But a self-reinforcing loop is a different animal entirely. A loop does not run out of fuel in the same way, because the loop is, in effect, building itself a bigger fuel tank as it goes. And the signature of a loop from the outside is exactly what we are seeing. It is escalation that arrives late. It is the strongest event coming on day 14 instead of day 1. A single empty pocket of magma cannot do that. Only a system that is still being fed, still cracking, still extending, still growing its own reservoir, can deliver its hardest punch 2 weeks into the fight. The 5.7 on the 22nd of May is, in that sense, a diagnostic. It is the loop showing its face. It is the clearest possible sign that the engine beneath Titan Ridge is not a single chamber emptying out, but a living, expanding network that has not yet found its ceiling. And the fact that we are still recording earthquake activity, that the 5.7 struck on the 22nd after 2 full weeks of eruption, tells us this loop is still running. The process is still active. Magma is still moving from the deep earth, from the upper mantle into the lithosphere, and then up and out. The engine beneath the floor has not switched off. If anything, it has just shifted into a higher gear. And that brings us to the question everyone actually wants answered. What does all of this look like from above? What is the satellite actually seeing? Because the view from orbit is telling us something that the depth charts say should not be possible. For all the precision we have, for all the instruments listening to the deep ocean and mapping every tremor, there is one thing we cannot do. We cannot see below the surface of the sea. It would be remarkable if we could simply watch the vent itself glowing on the ocean floor. But we do not have that. To put a camera down there, you would need a remotely operated vehicle, and you would need a ship parked directly above an escalating, energetic volcanic eruption, which is, to put it gently, not a place anyone wants to be. So our window onto Titan Ridge is the surface of the ocean, photographed from space, and it turns out the surface has a great deal to say. Start with the imagery itself. We have high-resolution satellite views of this eruption, including a remarkable set provided by NASA, captured as daily snapshots, one image roughly every day. Some of the close-up views are detailed enough that the scale bar on the image, the little marker that tells you how much distance the picture covers, represents only about 2 kilometers. That is a tight, fine-grained look at a remote patch of open sea, and in those images, several things stand out. The first is the plumes. Rising off the surface of the ocean, directly above the vent, you can see steam, water vapor, billowing upward. That is the eruption breathing. Hot volcanic material is meeting cold seawater, flashing it to steam, and that steam is punching up out of the sea and into the sky. The second thing is the discolored water. Spreading outward from the eruption site, the ocean changes color. That discoloration is a classic signature of submarine volcanism. It is caused by dissolved volcanic material, by fine particles suspended in the water, by the chemistry of the sea being altered around the vent. And in the imagery, you can watch that stain of discolored water spread. The third thing is the pumice. When a gas-rich volcanic rock is blasted out of a vent, it can be so full of frozen bubbles that it is lighter than water. It floats, and it forms what are called pumice rafts, drifting masses of volcanic rock riding on the surface of the sea. At Titan Ridge, pumice rafts are washing ashore on nearby islands. That is physical, tangible material from this eruption arriving on distant beaches. The volcano is producing so much rock that its output is making landfall. Now, here is where the satellites tell us something genuinely important, and it has to do with motion over time. Because we have those daily snapshots, we can line them up and watch the eruption evolve. And the evolution is unmistakable. Compare the image from the 17th of May to the image from the 22nd. In just those 5 days, the affected area, the footprint of plumes and discolored water, expands outward significantly. You can see it grow. And if you scroll back even further, to the 8th, the 9th, the 10th, the 11th, the 12th of May, you find that the eruption was already substantial back then. This was not a small event that slowly built up. It started significant, and it has been getting bigger. There has been some cloud cover over the region in the past several days, which has periodically made it hard to see clearly, and that is a genuine limitation. But in the windows where the clouds part, the picture is consistent. Expansion, growth, more. There is one more visual detail from the early days worth pausing on, because it is strange. When this eruption first began, observers noted an unusual feature, a kind of dual structure, where the eruption appeared to spread out and steam rose from both ends of it. 2 points of venting, not one. That anomaly was flagged when the event was first covered, and it is the kind of detail that hints the system feeding this eruption is complex and may have more than one pathway to the surface, which fits everything we just learned about the patchwork plumbing below. But the single most consequential thing the satellites are telling us is something they are telling us by contradiction. And to understand it, you need to know about depth. How deep is the vent? How far below the surface of the sea is the actual mouth of this volcano? This matters enormously because the depth determines how much the volcano has to grow before it can break the surface and become an island. And here our data is genuinely, frustratingly uncertain. The original bathymetry data for this part of the ocean, bathymetry being the mapping of the seafloor's shape, is low resolution. It is not high quality. Nobody has ever had a strong reason to map this remote patch of seafloor in fine detail. And that low resolution data suggests the vent sits deep, on the order of 1,000 meters, perhaps 1,300 meters below the surface. If that is true, the volcano would have to grow an enormous amount, vertically, to ever reach the air. And yet, the satellite imagery, those steam plumes, that discolored water, and in particular, the infrared signatures in the close-up images, the thermal heat signatures, are all suggesting something different. They are suggesting the eruption may actually be occurring much closer to the surface than that deep bathymetry estimate implies. There is a depth figure that comes out of the bathymetry context closer to 300 meters below the surface. 300 meters is a completely different situation than 1,300. So we have two datasets that disagree with each other. The old course map of the seafloor says deep. The fresh thermal evidence from orbit says shallow, or at least shallower, and that disagreement is not a footnote. It is one of the central open questions of this entire event. Because if the vent is sitting up near 300 meters and the eruption is escalating and it runs long enough, then a new island is not a distant fantasy. It is a near-term, plausible outcome, and whether the vent is deep or shallow, one thing does not change. An eruption powerful enough to throw a steam and ash column thousands of feet into the air while it is still submerged beneath the crushing pressure of the ocean is, by any measure, a tremendously powerful eruption. The depth changes the timeline. It does not change the force. Everything we have looked at so far points toward growth. A volcano stacking material upward, building a cone, escalating, possibly assembling an island. But growth in a structure like this carries a shadow. And the shadow is the reason this story has the word disaster attached to it. To understand the danger, you have to picture what a submarine volcano actually is as a physical object. It is not a neat, solid mountain. It is a pile. A steep, rapidly assembled heap of fresh volcanic rock, ash, and lava stacked up from the seafloor faster than gravity, and time can properly settle it. And steep piles, especially steep piles soaked in water and shaken by earthquakes, are not stable. They can fail. The specific failure that volcanologists worry about is called a flank collapse. It is exactly what the name says. A flank of the volcano, one of its sloping sides, gives way. A section of that loosely built cone detaches and slides. On land, a flank collapse is a catastrophic landslide, but underwater, a flank collapse does something land cannot do. As that mass of rock breaks away and slides down the slope, it shoves an immense volume of seawater out of its path. That displaced water cannot compress, and it cannot vanish. It has to move. And when a very large volume of water is suddenly displaced all at once, the result is a tsunami. This is not a hypothetical anxiety invented for dramatic effect. The Bismarck Sea, the very stretch of ocean where Titan Ridge is erupting, has a documented history of this. This region sits within a structure called the South Bismarck Sea Volcanic Arc, a whole chain of volcanoes, many of them submarine, strung through these waters. And that arc has produced not just big eruptions, but flank collapses, submarine landslides, the kind of slope failures that send debris fans sliding across the seafloor and generate waves. Historically, tsunamis in this part of the world, tied to these landslide events, have reached heights cited in the range of roughly 15, 20, even 30 feet. A 30-foot wall of water arriving on a low-lying coastline is a genuine catastrophe. So the hazard is real, it is specific, and it has precedent in this exact body of water. Now let me be careful here, because Titan Ridge has a particular geography, and that geography cuts in a reassuring direction. Compared to many of the other volcanoes in this arc, Titan Ridge sits somewhat farther out, more distant from the populated islands. Some volcanoes in this region are positioned terrifyingly close to inhabited land. If one of those produced a flank collapse, a tsunami wave could reach a populated shoreline almost immediately, with effectively no warning. Titan Ridge is not in that position. It is farther offshore, and it is at depth. The vent is below the surface, and a collapse originating from a submerged structure with that distance to the nearest islands gives the wave room and reason to lose some of its force before it ever reaches a coast. The depth and the distance are buffers. They do not eliminate the danger, but they soften it. Still, the risk is worth taking seriously, and it is worth picturing concretely. If you look at the bathymetry, the shape of the seafloor around Titan Ridge, you can reason about where a collapse would send its energy. If a flank were to fail on the northern side of the ridge, the displaced water, the tsunami, would propagate outward to the north. If a flank failed on the southern side, the wave would head south. The direction of the disaster depends on which face of the growing cone lets go. And which face lets go depends on where the structure is weakest, which is something we cannot fully see and cannot predict, because it is happening underwater, in a structure being built and shaken in real time. There is something almost paradoxical about a submarine flank collapse that is worth pausing on, because it runs against intuition. You might think that an eruption hidden under 1,000 meters of water would be safely smothered, its violence absorbed and contained by all that ocean above it. And in some ways, the water does buffer the eruption, but a flank collapse turns that same water into the weapon. The danger of a landslide on dry land is the rock itself, burying whatever lies in its path. The danger of a landslide underwater is not really the rock at all. It is the water the rock pushes. A submerged collapse converts a pile of failing volcanic debris into a moving wall of displaced sea, and that wall can travel across open ocean for great distances, barely losing height until it reaches a shoreline and rears up. The ocean that hides Titan Ridge from our cameras is the very same ocean that would carry a collapse outward as a wave. That is the quiet, uncomfortable mechanics of why a volcano you cannot even see from the surface can still reach out and touch a distant coast. And this is where the escalation we discussed earlier comes back to haunt the picture. A flank collapse becomes more likely as the edifice grows taller and steeper, and as the system absorbs more energy. We have established that Titan Ridge is doing both. It is building and it is energized. Those earthquakes, that 5.7 on the 22nd of May, are not just signs of magma movement. They are also stress, applied directly to a steep, young, waterlogged pile of rock. Every significant quake is a shove against an unstable structure. The very same escalation that makes the island formation exciting is the escalation that makes the flank collapse credible. The growth and the danger are not in tension with each other. They are the same upward curve. So how big could this get? It is natural to want a worst case, a ceiling. And the obvious reference point, the eruption everyone reaches for, is Hunga Tonga, Hunga Ha'apai. On the 15th of January, 2022, that submarine volcano in the Pacific produced the largest eruption of the 21st century, an event rated around a 5.8 on the Volcanic Explosivity Index, a blast so violent it sent a shockwave around the entire planet. So, is Titan Ridge a Hunga Tonga? Almost certainly not, and it is important to be honest about why. Hunga Tonga was a particular kind of volcano with a particular explosive potential. Titan Ridge is a submarine ridge volcano, and ridge volcanoes of this type do not typically carry that kind of cataclysmic explosive power. Expecting a Hunga Tonga repeat would not be supported by what we know, but here is the honest counterweight, and it is the line that should stay with you. There is far more about Titan Ridge that we do not know than that we do. The depth is uncertain, the structure is unseen, the duration is unknown, and a system this energetic, escalating this clearly, deserves to be watched, not because we are sure it will become something bigger, but precisely because we cannot yet rule it out. And to understand why this particular moment in time may matter, we have to lift our eyes off the sea entirely and look at the sun. Before we look at the sun, we have to settle the most practical question of all, the one that decides whether Titan Ridge becomes a permanent feature of the Earth or a footnote that the ocean quietly erases. How long will this eruption last? Because duration is destiny here. A short eruption builds a small pile that the sea wears back down. A long eruption builds an island. And submarine eruptions, particularly the kind that occur along ocean ridges and submarine ridges, have an enormous range of possible lifespans. Some of them are brief. They last only a few days, a flicker, and then they are over. But others, in these same kinds of environments, last for years. Not days, not weeks. Years of continuous or near continuous eruptive activity. That range is the whole ballgame, and the data we have been walking through, all of it, argues against the short end. An eruption that is escalating 2 weeks in, that delivered its strongest earthquake on day 14, that abruptly raised its hydroacoustic voice, that is visibly expanding its footprint in the satellite imagery, is not behaving like a flicker. It is behaving like the opening chapter of something long. It is entirely plausible that what we are seeing in late May of 2026 is the early stage of a long-duration eruptive process. And a long-duration eruption is exactly what an island needs. It needs time. Time for that cone to keep stacking material, layer on layer, lava and rock and ash, building upward from the seafloor. If the vent is genuinely closer to 300 meters down rather than 1,300, and if the eruption runs for months or for years, then the arithmetic of island formation starts to close. The structure gets the runway it needs to climb the last stretch of water and break into the air. This is the heart of what makes Titan Ridge worth your attention. We are not certain it will form an island. The depth is ambiguous. The duration is unknown. The structure is unseen. The eruption could, in principle, simply die out within a few days, and the honest scientific posture is to admit that. But the weight of the evidence does not point that way. The evidence points toward at least another week, 2 weeks, 3 weeks of this, and quite possibly towards something far longer. The kind of multi-month or multi-year process that genuinely builds new geography. Research cruises, ships sent out to take direct measurements at the site, are the obvious next step, and they are surely being planned. But until those measurements come back, We are reading this eruption from a distance, from orbit, and from sound, and what that reading shows is a volcano that is still going, still loading, still growing. So sit with the strangeness of that for a moment. There is a decent chance that somewhere in the Central Bismarck Sea, the map of the Earth is being redrawn right now. That a piece of land which does not exist today, which has never existed, is currently assembling itself out of molten rock and seawater. And if it breaks the surface, it will be one of the very few times in the satellite era that human beings got to watch an island be born from the very beginning. That is a rare and genuinely wondrous thing. It belongs in the same category as watching a star form or a canyon being carved, except compressed into a timescale a human being can actually witness across a few months of satellite images. And yet, you cannot hold that wonder cleanly because it is welded to the other thing. The same escalation, the same growing, energized, unstable pile of rock. The island and the hazard are not alternatives. They are the same volcano. Every day this eruption continues and intensifies. It does two things at once. It adds to the structure that might become land, and it adds to the stress and the steepness that could trigger a flank collapse and a tsunami. You do not get to root for one outcome and against the other, because they are driven by the identical process. To watch Titan Ridge build an island is to watch it become more dangerous. That is the genuine, unresolved tension at the center of this story, and no amount of data we currently have can tell us which way it breaks. There is one more layer to add, and it is the layer that zooms all the way out, beyond this volcano, beyond this sea, beyond the Earth itself. Because some researchers would argue that the timing of Titan Ridge, the fact that it is erupting now in this specific year, is not entirely a coincidence. They would point to a pattern that connects the behavior of volcanoes on Earth to the behavior of the Sun. It is an idea that has to be handled carefully, because it sits right on the line between real science and overreach. But it is a real idea, with real research behind it, and it is worth examining honestly. So let us go there. You already know the Sun runs on cycles. The most famous one is the 11-year solar cycle, the rhythm of sunspots and flares rising and falling. But the Sun has a longer, slower rhythm layered on top of that one, and it is less famous, and it is the one that matters here. It is called the Gleisberg cycle. The Gleisberg cycle is a modulation of solar activity that plays out over roughly 88 to 100 years. Think of it as a long, slow wave. Across that span of about a century, the overall energy of the Sun's activity gradually rises and then gradually falls. The 11-year cycle still ticks away inside it, but the Gleisberg cycle sets the larger envelope, the slow century-scale tide that the shorter cycle rides upon. Now here is the claim, and here is where it gets interesting. There is a body of statistical research suggesting that larger volcanic activity on Earth tends to be more common during solar minimums, during the low points of solar activity. And the research suggests this association is not limited to the short 11-year cycle. It also appears at the longer Gleisberg timescale. The two effects in this view sync up. When the Sun is in a quiet stretch, both on the short cycle and on the long century scale cycle, that is statistically when the Earth seems more prone to significant volcanic eruptions. And where are we right now? The argument goes like this. Earth is currently sitting roughly at the bottom of a Gleisberg cycle. We are in a relatively low stretch of solar activity on that century-long timescale, now beginning to climb back out of it, but still near the floor. And the people who take this pattern seriously point to a piece of supporting evidence that is hard to ignore. Hunga Tonga, the largest eruption of the 21st century, occurred in 2022, right inside this same low solar window. And now, in the same window, we are watching Titan Ridge escalate in the Central Bismarck Sea. To a pattern seeker, that lines up. It suggests we are living through a stretch of time in which large volcanic eruptions are statistically more possible. And Titan Ridge is one more data point on that line. I want to be very direct with you about how to hold this idea, because it would be easy to oversell it and it would be easy to dismiss it, and both of those would be wrong. Here is what is true. The Gleisberg cycle is real. It is a genuine, named, well-documented feature of how the sun varies, not a fringe invention. And the statistical correlation between solar minimums and volcanic activity has genuinely been studied in the scientific literature. This is not nonsense. It is a real line of research. But here is the equally true, equally important, other half. A statistical correlation is not a proven cause. The fact that two things tend to happen around the same time does not mean one is making the other happen. The proposed physical mechanisms, the actual chain of cause and effect that would let the sun's century scale mood reach down and influence magma deep inside the Earth, remain debated and unproven. Nobody has nailed down how that would physically work, or even established for certain that it does. So here is the honest framing, and it is the only responsible one. The solar volcanic connection is an intriguing statistical pattern that some serious researchers take seriously. It is worth knowing about and worth examining. But it is not a confirmed cause and effect law, and you should be skeptical of anyone who presents it as one. And critically, Titan Ridge does not need the sun to explain it. Everything we have walked through in this video, the pulse of magma from the upper mantle, the patchwork plumbing of melt lenses and mush zones, the earthquakes cracking and extending the system, the escalation, all of it is fully explained by ordinary, well-understood volcanic processes happening inside the Earth. You do not need a solar trigger to account for what Titan Ridge is doing. It is an arc volcano being fed by the planet's own interior, behaving exactly the way the geology says an arc volcano can behave. The Gleisberg pattern is a fascinating piece of context to hold in your mind. It is not the cause of this eruption. And while we are being honest about uncomfortable questions, let us address a smaller one that some of you are probably thinking. If Titan Ridge is the largest volcanic eruption of 2026 so far, possibly building a new island, with a genuine tsunami hazard attached, why is it not dominating the headlines? Why is this not everywhere? The answer is not a conspiracy, and it is not suppression. The answer is geography and physics. This volcano is remote. It is in the open ocean, far from cameras and crowds. It is submarine, which means there is no dramatic river of glowing lava for a news crew to film, because the eruption is happening underwater. And being near the eruption to film anything is genuinely dangerous, which is why there are no thrilling shots from a ship's deck. The quiet around Titan Ridge is not someone hiding it. It is simply the natural quiet of a powerful event happening in one of the hardest places on Earth to observe. The story is huge. The location just makes it hard to see. Which brings us, finally, back to the only question that actually matters. So here we are, at the end of the picture, and it is time to put every piece on the table at once and look at the whole thing. What is actually happening in the Central Bismarck Sea is this. A submarine volcano called Titan Ridge began erupting on or around the 8th of May, 2026. It announced itself with an earthquake swarm, a tight cluster of magma-driven quakes. And then, instead of fading the way most of these eruptions do, it escalated. It delivered its strongest earthquake, a magnitude 5.7, on the 22nd of May, 14 days in, a single event carrying as much energy as the entire swarm before it. It abruptly raised its hydroacoustic voice on the 20th. Its footprint is visibly expanding in the satellite imagery. By every independent measure we have, sound, seismicity, and sight, this eruption is getting stronger. And that escalation forks into two futures. And the hardest truth of this entire story is that they are the same future, seen from two sides. On one side, there is the island, a long, sustained, escalating eruption, possibly venting from much shallower water than the old seafloor maps suggest, is exactly the engine that builds new land. Cone stacked on cone, layer on layer, climbing toward the surface. If this eruption runs for months or for years, the Earth may gain a piece of itself that has never existed before, and we may get to watch the entire birth, which has happened only a handful of times in the era of satellites. That is the wonder. On the other side, there is the disaster. The same growing, steepening, energized pile of fresh rock is an inherently unstable structure, and the Bismarck Sea has a documented history of flank collapses, submarine landslides, and the tsunamis they generate, with historical waves in the range of 15 to 30 feet. Every significant earthquake is a shove against that unstable cone. The very growth that might build the island is the growth that loads the collapse. Titan Ridge's distance from the populated islands and the depth of its vent are real buffers, real reasons the worst case is softened. But the hazard is genuine, and it is the reason the word disaster belongs in this story at all. Here is what we do not know, and the list is long, and it is honest. We do not know the true depth of the vent, with estimates ranging from a relatively shallow 300 meters to a deep 1,300. We do not know how long the eruption will last, with the possibilities spanning from a few more days to several years. We do not know the internal structure of the cone, or which flank, if any, is closest to failing. We do not know whether it will break the surface, or slide into the sea, or simply continue as a powerful submarine eruption that does neither. There is, genuinely, more that is unknown about Titan Ridge than is known. Research cruises will eventually go out and take the direct measurements that begin to close those gaps. Until then, we are reading this volcano from orbit and from the sound it pushes through the water. But step back from the list of unknowns and look at what is not in doubt, because it is striking. It is not in doubt that Titan Ridge is, very likely, the largest volcanic eruption anywhere on Earth so far in 2026. It is not in doubt that it launched a steam and ash column some 9,000 feet into the sky while erupting beneath the crushing weight of the ocean, which means it is a tremendously powerful eruption, regardless of how the depth question resolves. It is not in doubt that it is escalating, because 3 independent instruments all say so. And it is not in doubt that it sits in a part of the world, the Western Pacific, the Ring of Fire, that has been releasing an enormous amount of energy lately, through earthquakes and through volcanoes, energy that is expressing itself in event after event. So the real question at the center of all this is not whether Titan Ridge is building an island or loading a disaster. The real question is harder, and it is this: what does it mean that we cannot tell the difference yet? That the birth of new land and the trigger for a deadly wave look identical from the outside, that they are driven by the same rising curve of energy, and that the only thing standing between us and the answer is time and a few measurements we have not taken yet. The Earth, in the Central Bismarck Sea, is in the middle of a sentence. It started writing it on the 8th of May, and we are standing here, watching the ink go down, with no way to know whether the sentence ends with the word island or the word disaster, until the planet finishes it for us. The only thing the data tells us for certain is that it is still writing, it is pressing harder, and it has not reached the end.